Excellent. So, welcome everybody. Good afternoon. Welcome to this talk on sustainability and circular economy in the aluminium industry. Just firstly to say that this talk is being recorded, so it can be viewed afterwards as well. And my name is Dr. Michael Kenyon. So I work at a company called Innoval Technology. We are a consultancy to the global aluminium supply chain. And this talk is actually as part of a webinar series on sustainability and circular economy. So every month we have a talk that is based on a foundation industry, whether that's metals, ceramics, paper, cement. So we had a talk last month that was based on the steel industry, and that talk was recorded as well and is available. So I will put some of the links in the chat towards the end on the different webinar series talks that have already been conducted, and we have a few more upcoming every month as well. So this talk is going to consist of initially setting the scene in terms of the global greenhouse gas emissions. And then we're going to break that down into the contribution from the aluminium industry. And I'll go into a bit of detail about the primary production of aluminium, as well as a little bit about the secondary production route. And then we're going to reset the scene in terms of the emissions targets that the global industry needs to achieve to be in line with some of the climate change targets that have come out of the recent COP conferences, some of the agreements in the Paris Accord as well. And I'm going to talk about the solutions that need to be put in place across the global industry to achieve those targets. I also want to give some examples of what the industry is actually doing at the minute in order to achieve those targets. It's all well and good producing a pathway and highlighting the solutions, but is the industry actually investing and implementing some of those solutions? So we should have time at the end for a bit of an open discussion, some questions. It'd be good to hear some other opinions as well. So first, we're going to set the scene in terms of the global greenhouse gas emissions. So this particular figure on the left, I just wanted to highlight from a global standpoint across all sectors where those emissions ultimately lie. And you can see in this particular figure is from 2016. And the total greenhouse gas emissions was around 50 billion tons of CO2 equivalents. And I've highlighted a box in the top right-hand corner of that figure, where around 10% of those emissions actually come from the production and use of energy in industry, and specifically the steel and aluminium industries. And I've got some more absolute figures in the table on the right. So you can see the aluminium industry contributes around 2 to 2.5% of global greenhouse gas emissions as of 2018. Steel industry around 6.5, 7.5%. Now I work specifically in the aluminium industry, and that's where we're going to base this talk. Again, if you want to see a similar talk around the steel industry, a previous speaker last month gave that talk, and I'll put that link in the chat afterwards. In terms of the aluminium sector emissions, essentially, unsurprisingly, most of those emissions occur from the primary production, and I'll go into a little bit of detail in a minute on the exact process routes within the primary production. But I've highlighted the breakdown within the primary production in this red box on this chart. So this particular chart was produced by the International Aluminium Institute, among some other consortium as well. Many of the figures in this talk have been produced by the International Aluminium Institute and the European Aluminium as well. And it's only due to the really good work that those guys do in collecting the data that has allowed a pathway to be made in the first place. So there's a lot of credit to those organizations in this talk. If we break that emissions down in terms of the primary production, you can see that of that 1.1 billion tonnes that is contribution from the aluminium industry, the majority of that is actually associated to the electrolysis stage in primary production, the smelting stage. But we also have some contribution from refining of the bauxite to alumina, as well as the anode production, a very small contribution from the casting relative to the other operations as well. But within the 1.1 billion tonnes from the global aluminium industry, we also have semi-fabrication, so the rolling, the extrusion, and the secondary industry as well, so the recycling industry. And we'll talk a bit about more the recycling industry later. So looking specifically at the primary production route and understanding where those emissions come from, first we initially start with the mining of the bauxite ore, which is a reddish clay material. And in terms of greenhouse gas emissions, the mining actually has a relatively low contribution overall, but of course with mining there are other environmental impacts that are really important to consider, such as resource depletion and land use. But once we've mined that bauxite, we need to refine it to alumina. So bauxite contains a high content of aluminium. We need to extract that first into its aluminium oxide form, alumina, through the Bayer process. So the main contribution to greenhouse gas emissions within the Bayer process is mainly from the thermal energy requirements, where the bauxite is heated in a solution with sodium hydroxide. It's fed through a system to remove some impurities. It's then washed and cleaned and eventually dried, again requiring a thermal energy input to produce a pure white powder, which is alumina. So one of the main other considerations environmentally from the Bayer process is the main waste output, which is red mud, bauxite residue, which can be toxic. However, significant quantities of this have been used in the construction industry and cement industry, but the waste management of bauxite is a key environmental impact for the industry. Moving to the next stage, so we have our white powder, our alumina. Now we come to the smelting, the whole Héroult process. And it's really the electrical intensity of this process where most of the emissions come from. So actually within the primary production route, around 75%-ish of the emissions occurs from the use of energy for the smelting stage. And this is because we need to reduce that alumina to aluminium and oxygen. And this is done in an electrolytic cell or a pot. An example is given in the figure here of a number of electrolytic cells. And what happens in this system is you have a cathode and an anode, and the alumina is added to a molten electrolyte at around 960 degrees. When electrical current is applied through the system, the alumina is reduced to pure aluminium and oxygen. Now the oxygen combines with the carbon anode, producing CO2 as a direct byproduct of the smelting stage. Then we have the molten aluminium, which is siphoned off and cast into ingot form. So as highlighted, it really is the electrolysis stage that the major contribution to greenhouse gas emissions occurs, among other areas within the global industry as well. And again, the International Aluminium Institute, with some data from the International Energy Agency, have actually modeled the reduction in emissions that is required to achieve the targets set out in many of the climate change legislation, in many of the conferences, the recent COP26 conference. And in essence, what we need to try and do is to keep temperature warming to below 2 degrees versus pre-industrial levels. And this is called the beyond 2 degrees scenario. And that isn't net zero per se, that is just to try and limit the temperature warming to below that 2 degrees. And actually more recently, that has come out of mainly COP26, that target really needs to be to below 1.5 degrees. And I'll be touching on that in a few slides. But if we have a look at the modelling that was done to consider the emissions that would be, in essence, allowed within the industry among the breakdown of these operations, and this would be incorporating a lot of the solutions that I'll be discussing later on. You can see, for example, that the electrolysis stage, the greenhouse gas emissions, drops to almost nothing relatively to where we are today. And among the other contributions as well, such as thermal energy, and even in the secondary aluminium production from end-of-life scrap, that the contribution of greenhouse gases from that production needs to reduce as well. So overall, if we have a look in the bottom right-hand corner of these two tables, which gives the global greenhouse gas emissions for the industry, where we are in 2018, 1.1 billion tonnes, we need to reduce that to 250 million tonnes, which is a reduction of 77%. And that's while maintaining forecast growth within the industry of 80%. So it's quite a daunting target. Now, I've highlighted that at the minute, the main contribution occurs from that electrolysis stage, and it's actually the source of energy, electrical energy, that's required that is contributing to those greenhouse gas emissions. So under that modeling, again, they looked at what the breakdown of energy source would be in order to keep that temperature rise to below 2 degrees. And that's represented in this figure here. So you can see where we are today. There's predominantly coal-based, fossil fuel-based energy source for the smelting power mix. We have some renewables in there, mainly hydro and nuclear. Nuclear, not renewable, but it's a clean source of energy, a cleaner source of energy. And we have a contribution from natural gas as well. Now, in order to hit those targets, you can see in the right-hand column that we need to, it's unsurprisingly, significantly reduce that dependency on coal and natural gas for the energy source for the smelter power mix globally. And again, this is to achieve that target of temperature rise below 2 degrees. And in combination with that demand increase for primary aluminium of 80%, which I've given an example of on the left-hand side here. So this is a figure from the European aluminium. You can see here the demand for primary aluminium, how it has increased over the past 20 years and is forecast to increase over the next 30 years. And that's across most major markets that aluminium is used for: transportation, construction, engineering, consumables as well. And to really put that side by side in terms of the emissions reduction required, we've already seen the beyond 2 degrees scenario, which is given by the yellow line in the right-hand figure. But more recently, they've also done additional modeling looking at the 1.5 degree scenario. So that, again, keeping temperature warming to below 1.5 degrees. And we need to reduce those global emissions down to 53 million tonnes. That's from 2018 value of 1.1 billion tonnes. So I'm just going to break that down a little bit further in terms of the primary production and the secondary production. There's going to be quite a few, well, it's going to be 5 graphs on this slide, so I'm just going to split it up into primary and secondary industries and what the sort of allowed contribution from those industries will be in terms of production and emissions. So if we first have a look at this top left-hand figure, under the 1.5 degree scenario, the primary aluminium production as of 2018 is 64 million tons, and that would have to increase up to 68 million tons in order to achieve the 1.5 degree scenario. Now that's in combination with the reduction in emissions from that process route. So in 2018, per ton of aluminium, a global average is 16.1 tons of CO2 per ton of primary aluminium produced. Now we need to reduce that all the way down to 0.5 tons per ton by 2050, which is quite a significant reduction in emissions per ton of aluminium produced. And we'll talk about the solutions that are required for that over the next few slides. But that's the situation for primary aluminium production. But that is in combination with the secondary aluminium production route, the recycling of end-of-life scrap and pre-consumer scrap as well. So if I have a look at the production of end-of-life scrap, post-consumer scrap in this middle figure here, historically this has increased quite a lot over the past 20 years, the use of end-of-life scrap, and we need that to continue for the next 30 years, up to around 68 million tons within the global system. And again, that's in combination with reducing the processing emissions associated with recycling aluminium. So again, as of 2018, those emissions for recycled aluminium, about 0.6 tons of CO2 per ton of secondary aluminium produced, and that needs to be reduced down to about 0.1 tons per ton. And then we come to pre-consumer scrap. So that's the scrap that is produced through semi-fabrication, for example. And we need to reduce or increase our process efficiency, so reduce the overall amount of pre-consumer scrap that is produced. And of course, any pre-consumer scrap that is produced, because it is unavoidable, should be 100% used straight back into the system, as it is the cleanest type of scrap, as you said, of a known composition and of a known process history. So in terms of keeping temperature warming to below 1.5 degrees, this is the situation in terms of the primary production and secondary production routes for the next 30 years, the targets that will need to be achieved. So how are we going to do it? Because it is, in my opinion, quite a daunting task in order to achieve those targets. Well, again, in combination with the modelling, the Institute of Aluminium and other aluminium organisations have highlighted the solutions that would need to be put in place and that have been put into these models as well. And in essence, there are the three main pathways. So we have electricity decarbonisation, which we've already touched on a little bit, direct emissions reductions from the primary process production route, and we also have recycling and resource efficiency. And I think it's important to say that all these three pathways need to be applied in combination. No one pathway alone, even if the entire industry was to incorporate it, would be enough to achieve those emission reduction targets. So they have to be employed globally, and they have to be employed universally across the industry. So I'm going to go into a bit of detail about some of these solutions, mainly the solutions that we can incorporate now as of tomorrow. And I'm not going to really touch on some of the other solutions that are in the pilot stage, or maybe a couple of decades from being utilized on a commercial scale. So renewable energy, we've already touched on this. I'm sure everybody is already fully aware that we need to be using more renewable energy, not just for primary aluminium production, but across the full supply chain. But I just wanted to show what the effect in terms of some of the absolute numbers of using just renewable energy for primary production. So this particular figure shows the effect of using predominantly fossil fuel sources such as coal-fired or gas-fired. So that might represent historically China or the Middle East in terms of the energy that those smelters would use. And then we also have more mixed grid, maybe the EU and the UK, a higher fraction of renewables, but also still a dependency on natural gas and a little bit on coal as well. But then we see on the right-hand side, if you can use 100% renewable energy source, that contribution to emissions per ton of aluminium really comes down. And the contribution is relatively minor compared to then some of the other emissions from, say, the direct process, the thermal energy required, as well as the transport and ancillary materials as well. But just as a reminder, again, even using 100% renewable energy source alone for primary aluminium wouldn't get you down to that 0.5 tons per ton we need to achieve by 2050 to achieve that target of keeping temperature warming below 1.5 degrees. But it's one of the biggest steps we can do, and it's something we can do right now. So a lot of text on this slide, so I'm going to go through some of these points one by one, but this is talking about pathway number 2. It's actually pathway 3 on my previous slide, but very, very important subject is aluminium recycling and moving towards a more circular economy. So I'm just going to talk about some of these stats that the industry uses quite a lot. First bullet point here, and this is just quite an obvious statement, but it's always good just to reiterate that recycling aluminium only requires 5% of the energy compared to the equivalent amount of primary produced aluminium. And because of that, because there's no dependency on smelting or refining of bauxite to alumina, the emissions are also significantly reduced by around 95% or more. So that really just states in that one point that we need to be increasing the amount of end-of-life scrap that we are using. And generally, end-of-life scrap in terms of the economics is cheaper than primary aluminium, depending on the quality. Some scrap streams, maybe like lithographic scrap, which is highly pure scrap, might be quite close, maybe even a little bit more expensive than primary, but not too much more. You might have some what you might call dirtier scrap streams that are quite far away from the composition that you're trying to achieve. They will be significantly cheaper than primary aluminium. So there's a broad range of prices that scrap streams can attain depending on their quality. Another statistic that not just the aluminium but steel as well like to throw around is that metals are infinitely recyclable, which yes, they are in theory. What does that mean? It means that you can melt and cast the material over and over again without inherently losing the material properties. In reality, at the end of life, when the product is collected and shredded and sorted, no sorting operation is 100% efficient. There's going to be some impurities in there that ultimately changes the composition that you're after. There's going to be mixed grades in there as well, and there's always going to be, at least in the present, some dilution of the material that might be required in order to get it back to that original state. Finally, 75% of aluminium ever produced is still in use today, which is great. We want to use these materials as much as for as long as possible within their lifetime. And then I'm just going to touch on a few of the caveats. I've already talked about the fact that depending on the scrap stream, the quality of the scrap stream might mean that more work is required to bring it into the specification for the application that you want to use. And some alloy systems have a tighter specification or lower tolerance to impurity elements, which might mean they can't use as much scrap. So it's really important that the industry invests in sorting technologies and in improving the separation and segregation of the different alloy grades. And final point, I just want to touch on the fact that yes, 75% of all aluminium ever produced is still in use today, which is fantastic. That means that in the future, there should be a fairly abundant source of end-of-life scrap. And you see the figure in the bottom right is an example, a forecast of the end-of-life scrap that will become available over the next 30 years. So it'll increase from around 20 million tons today up to around 60 million tons. And that the main source of that scrap will come from mainly, well, at least in the extrusion industry, from buildings, for rolled products, automotive and cans, and for castings, again, automotive products as well. And we need to utilize as much of that end-of-life scrap as possible. But something to keep in mind is that a lot of applications do have a longer lifetime, especially architectural construction applications, means that scrap, it won't be available for maybe a few decades. I've also included here a figure that just shows a bit of a breakdown as to the regional mix of aluminium in terms of primary production and secondary production. So secondary production can be further split into end-of-life scrap and also pre-consumer scrap as well. And you can see the global average in the right-hand column as of, again, around 2018. So 66% of all aluminium produced could be associated from a primary source, whereas around 34% from a secondary. And that does vary region on region. So we talk a little bit more about some of the, details on the separation technologies, the sorting technologies that can be used for aluminium. So let's take an example of an end-of-life vehicle. Some of the components of that vehicle might be taken off before it's crushed and shredded, maybe the wheels, some of the engine block components. Ultimately, a lot of the vehicle will be shredded. Firstly, we have to separate the metals to the glasses and the plastics. And then once we have the metallic fraction, we'll separate magnetically the ferrous and the non-ferrous metals. So then we might have a stream of aluminium, and we can further separate that using technologies such as X-ray fluorescence, X-ray transmission, or even laser-induced breakdown spectroscopy. So LIBS is particularly efficient at separating some of the more distinctive alloy grades, even within the 6000 series family or 5000 series family as well. And incorporating some of these systems is going to be key into developing scrap streams closer to the composition that you're after. And I just wanted to give an example of a bit of a case study on the fact that you can produce alloys that do have low tolerance to impurities or tight specifications from a lot of end-of-life scrap. So this particular study, which was a government-funded study that Innoval was a part of, it was called Reality. It was a few years ago now. We had a number of consortium on board, including Jaguar Land Rover, Axiom Recycling, Novelis, ourselves, and a couple of universities as well. And this case study really looked at the taking sometimes quite a dirty scrap stream that might have quite a mix of alloy grades, using advanced sortation methods, melting and casting, and developing that material to achieve the material properties of the original component, equivalent made from primary produced material. So again, this project really covered the full cycle of that scrap, and if I remember rightly, did achieve producing some 6000 series for automotive applications. Sorry, that was from 50, 75%, and even 100% end of life scrap. So that was just touching on recycling and the importance of increasing the use of end-of-life scrap now and in the future. Come to my next pathway, which is direct emissions reduction. So as I mentioned earlier on, within the electrolysis stage, the oxygen that is reduced from the alumina combines with the carbon anode, and CO2 is a direct byproduct of the electrolysis stage. Now, for a number of decades, inner anode technology has been researched, but I think it's only more recently, or in the recent decades, where significant investment has allowed that technology to really be developed and be used on a commercial scale. So I've included here the company called Alesis, who is developing inner anode technology. So this technology will replace the carbon anodes in existing smelters. And it's claimed that this technology will eliminate the direct CO2 emissions from smelting and actually releases oxygen as a byproduct. And I just put a couple of articles up, very recent articles, to show that this is really at the forefront of trying to reduce the emissions within the global aluminium industry. So here, this top article here is from the 1st of March. And we really are getting to the stage, I think, where this technology can be used commercially and really at the high production volumes that we see globally now. So much so that some of the large Goliath companies are really exploring using aluminium that has been developed utilizing this technology. So, for example, here, Apple have highlighted their collaboration with Alesis on this technology, among a few other large companies as well. But it's not just inner anode technology that comes under direct emissions reduction. We can talk about carbon capture technology. This can be applied across numerous industries, not just aluminium. But again, I just wanted to highlight that this technology is being invested in the aluminium industry. Article here from the 21st of March this year, so a couple of weeks ago. Hydro investing in carbon capture technology to eliminate emissions. And also, I'm not going to talk about hydrogen, but because I think that's something for the future. That's not something we can use right now at the scale we want to employ it for the global aluminium industry. And there's also many other industries that are looking to use green hydrogen as well. So I think that's one for the future, in my opinion. And I think in terms of putting the infrastructure in place to supply the amount of green hydrogen that we would want to use is at least a minimum 5-10 years away. So again, I just wanted to highlight here that what is happening right now. I mean, we hear almost on a daily basis that we really are at the point of no return in terms of putting significant action in place to help reduce our emissions to achieve those targets. And I just wanted to highlight a few things to show that at least I think the aluminium industry is moving in the right direction, as well as some other metals industries as well. And I think having these pathways so clearly out there really helps the industry in incorporating these solutions. So in terms of pathway 1, this particular figure shows the global power mix used for the aluminium industry. I think this is for the smelting specific power mix. And I haven't put the legend on here, but the brown bar is coal-based energy source, and the blue, yellow, and purple are renewables, and the blue is hydro. And all I wanted to show here is that over the last 5 or so years, the increase in renewables, so the yellow bar, and the contribution from hydropower is increasing, and the contribution from coal and natural gas is decreasing. So things are changing, things are moving in the right direction in terms of electricity decarbonisation. And some really good examples online of this, and some of the OEMs that are trying to really incorporate this into their systems. So this one particular example highlights BMW Group, who have sourced a lot of aluminium from the Middle East, where we are now seeing these giant solar farms, and which some of them are dedicated to providing energy for smelting operations. So that's a really positive thing to see, and we need more of that. Again, I've already touched on direct emissions reduction, people investing in anode technology, trying to progress it to the really to be used for the high volume productions that we need, investing in carbon capture technology. I refer back to this graph in terms of recycling. You can see historically in terms of post-consumer scrap, again, things are moving in the right direction. We are using more and more, and we just need that to continue, if not accelerate, ideally, in the amount of end-of-life scrap that we are using. And many companies are now evaluating their entire portfolio in terms of trying to introduce alloys that specifically have a higher recycled content, whether that's hopefully mainly end-of-life scrap content, but will ultimately also incorporate some pre-consumer scrap. Just as an example, Hydro have a range of alloys, Reduxa and Circal, and Novelis also have starting to build their portfolio, and Constellium, and many of these large aluminium companies are really starting to put their recycled content alloys on the market. And some of them even give some absolute figures in terms of at least a cradle to gate footprint in their primary aluminium. So whether that's 4 tons per ton of a particular alloy portfolio, or even lower than that. So I'll come to my final slide and closing remarks, really, in that we know the aluminium industry needs to reduce its emissions by at least 80%, and that's just for the beyond 2 degrees scenario by 2050. Ideally, it needs to be up at 95% reduction to achieve that 1.5 degree scenario. And that's while maintaining steady growth of around 80% for the next 30 years. So we're going to have that dependency on primary. So we need to incorporate those solutions into that process route as well. So just highlighting where we are today, relatively greenish maybe. We need to responsibly source our primary aluminium from sources that typically use renewable power sources, trying to incorporate as much end-of-life scrap as possible, investing in those sorting technologies. In the future, I've put lower carbon primary. So again, maybe some primary production that is starting to incorporate the inert anode technologies, the carbon capture technologies, still increasing our use of end-of-life scrap and closing that loop in terms of a more circular economy. And then at 2050, we know what we need, we know where we need to be. We need to have primary aluminium that really has a significantly low footprint compared to where we are now. So we're talking at levels 0.5 tons of CO2 equivalents per ton of primary aluminium. We need to maximize our use of end-of-life scrap content. That involves optimizing that secondary metal supply chain, and the quality scrap streams need to be developed, as well as incorporating those inert anode technologies, more carbon capture technologies. Altogether, all those solutions need to be made in combination. So thank you very much. We've got a good 15 or so minutes left, so I'll happily take any questions or comments or open discussion on this topic. If you'd like to raise your hand, and now I'll come to you. Or feel free to unmute and ask a question directly.
Hi, Michael, there's a question in the chat for you.
Oh, yeah. Let's have a look. So the question, I can't see the question in the chat. Could you read it out, Helen?
For direct emissions reduction, what combination do you think CCUS will play? What is the breakdown between CCS and CCU?
Great question. My honest answer is I don't know, because I think it's not a technology that I've looked too much into. Just like a little bit like the hydrogen, I think it's a technology that is still relatively in the pilot stage and is starting to be incorporated on a larger scale, but it might take maybe 5 or 10 years to really incorporate that on the levels we need to see any significant reduction in emissions from that solution alone. So yeah, I would need to look into that technology a bit more to answer that question. So are there any other questions from anybody else? Well, what I will do is I will put a link to the webinar series in the chat. So as I mentioned, this is part of a wider webinar series on sustainability and circular economy in the foundation industries. This is based on the metals industry, but mainly aluminium, of course. We had a talk on steel last month, which was recorded as well. So that can be found on the link I just posted in the chat. And unless there are any other questions or comments, Paul, I can see Paul Lansdell has a question.
Yes, Michael, I've got a question. What effort is the nuclear industry making to provide localized electrical power supplies for the big consumers? Rolls-Royce were talking about building the power units that are going to nuclear submarines to actually act as a supplier for high energy users. Is there anything moving there? Because that seems to be a sensible way of supplying lots of electricity to the big consumers.
Yeah, good question. Again, I think, not specifically on the nuclear industry. All I'm aware of really is what's put out there in the general news. So obviously our own government, the UK government, have stated their investment in nuclear in the future, which will contribute to the overall grid mix. Now, many smelters take their energy from the grid mix, or some have dedicated power stations as well. I don't know whether any larger smelting operations are thinking about getting a larger contribution from nuclear. That's something that I have to look into. But you're right. I mean, there is large investment in nuclear occurring, not just in the UK, but globally, and that will contribute to the reduction in emissions for the grid mixes, of which many smelting operations take their source from. But to answer your question specifically around applying specific nuclear operations to smelters, I'd have to look into that one as well. So are there any other questions from anybody else?
There's another one in the chat. What is the difference in CO2 emissions from better process control compared with the current industrial practice?
Sorry, say that again, Helen.
What is the difference in CO2 emission from better process controls compared with the current industrial practice?
So better process controls.
Yeah.
Yeah, so in that regard, better process control, or even better alloy development to reduce, say, process scrap, ultimately will reduce our dependence on primary aluminium a little bit. So if we can improve our efficiency in terms of losses from melt, and reduce the amount of process scrap produced, then we don't need to produce as much primary aluminium in the first place. In terms of absolute numbers, where you can see the in this talk, you can see the tons of CO2 produced per ton of primary aluminium. And if you look at some of the semi-fabrication operations, such as extrusion and rolling, which can produce a fair amount of pre-consumer scrap, you can put those two together and directly see that as a percentage reduction in the amount of process scrap reduced, you could work out exactly how much CO2 you might save by not having to produce as much primary production. So that's something you could look into as well. Okay, so are there any other questions?
If I could, Michael, I would like to ask a question.
Absolutely.
I run a research business, and one of the things that I've been looking at is actually the recycling of difficult aluminium scrap back into high purity alumina, right? Which obviously has its own CO2 savings in that it obviates the need for mining bauxite and processing bauxite into alumina. And it seems to me, I've punched a lot of figures, that this is actually for some particular classes of scrap, fines in particular, which, as you know, are difficult to smelt. And it also has the advantage of in making the scrap fines back into bauxite or high purity alumina. In actual fact, you actually produce enough hydrogen to smelt a lot more scrap. In other words, if you have a smelter that, say, takes a 5-ton charge, then if you sacrifice a ton of fines that may have gone into that charge, to make hydrogen and high purity alumina, then you can smelt the other 4 tons with it. It's and consequently, you have a zero emission smelter that's producing a very valuable product. Do you see any future for this kind of technology, though? I found it difficult to get anybody seriously interested. It sounds like magic, but it's not. It's very straightforward and reliable process chemistry, which you can find in the literature going back 50 years or more.
Yeah, no, as you say, that sounds, you say, almost too good to be true. And again, that's not something I'm too familiar with, so I'd have to look at some of those research papers. But it doesn't surprise me that research does go back so far. You tend to find in the aluminium industry that things do tend to go round and round. So a little bit like the inner anode technology has been researched many years ago, well before my time. And it's only really through significant investment, and you say trying to get people on board, that has allowed it to progress to a stage where it's commercially viable. So sometimes you're right, it's not just the technological barriers, but it's the getting the awareness out there and getting some of the investment behind it to really see it through. So I don't envy your challenge, Alan, but yeah, no, it sounds fascinating. I'd be quite interested to see some of those papers if possible, Alan.
Well, perhaps we could do that, after the webinar.
Yeah, absolutely. Yeah, I'll not a problem. That would be great.
I'll drop my company website into the chat. And
Brilliant. Thanks a lot, Alan.
No, thank you. It's not often that you hear a presentation by somebody with such a Catholic approach to the whole, by which I mean all embracing, approach to the whole industry, actually, from hole in the ground to motor car and beyond. It's very interesting. Thank you.
Yeah, no problem. I hope everybody found it useful. Any other questions from anybody? Thanks for that, Alan. Just seen, I'll copy that. And yeah, I will be in touch
Thank you.
about that technology. Thank you very much. Well, thanks everybody. Thanks for joining. And say if you want to watch this recording back, it will be available online on the link I posted in the chat. So thank you very much, and I'll end the webinar here. Thanks everyone.
Thanks, Michael.